This tutorial looks at the storage of carbon. We've seen that there are a number of processes that will move carbon from the atmosphere into another sphere in the carbon cycle. So these storage sites are sometimes referred to as sinks or reservoirs, and these reservoirs could provide a long-term storage site or a short-term storage site. So that's what this tutorial is about. First of all, we're going to look at fossil fuels as a deposit or storage site for carbon. And there's quite a bit of information on some of these slides, so what you might want to do is pause them so you can read the text as well. I'm sure you already know about fossil fuels, but we'll just recap here. Fossil fuels are found in the Earth's lithosphere. So they could be found on land, the terrestrial environment, or they could be found in the oceans. So what are fossil fuels? Well, typically they're phytoplankton, microscopic plants found in the oceans and bodies of water. Maybe some smaller organisms as well, referred to as zooplankton. So a lot of these plants and animals have an aquatic origin. But fossil fuels could come from trees and shrubs too, that have died and fallen over into swamps. What's key is that these plants and animals are buried underground, and it takes them hundreds of millions of years to actually change from that organism into a fossil fuel, into a hydrocarbon. So what's key is this process of sedimentation. So in this ocean environment we have plankton, phytoplankton and zooplankton, largely microscopic organisms falling to the bottom of the seabed. Here of course they begin to get decomposed by the decomposers, the bacteria and the fungi. But before the decomposers can basically break them down fully, there are layers of sediment that fall on top. And as those layers build up, our planktonic organisms change. They become fossilized and they're storing those hydrocarbons that we're digging for right now. So this is a geologic process, and it takes hundreds of millions of years to form coal, oil and gas. So let's have a look at some coal deposits in Antarctica. So as we know, the dry valleys are not all covered by snow and ice, quite an unusual location. And if we have a look at these rocks, we can see coal seams in the rocks, really quite obvious here. So how on earth do we have coal in Antarctica? Antarctica hasn't always been a cold, icy continent. As I'm sure you're aware, we have Gondwanaland sitting up by the equator, and this broke up, and through tectonic plate action these continents have moved around. So we now have Antarctica in its current position, and even for some 30 million years I think, as Antarctica sat at the South Pole, there were forests on Antarctica. So Antarctica would have had a temperate climate. So before Antarctica froze over, this temperate climate allowed plants, trees, shrubs and even dinosaurs roamed around the continent of Antarctica. And one of these fossils was a 6-foot tall penguin, so you can have a look at that, quite an extraordinary creature. And of course, where we have this plant life and also the microorganisms or phytoplankton and zooplankton around the Southern Ocean, we've got an opportunity for coal and oil to be deposited. So school textbooks have told us that fossil fuels are non-renewable. Well, that's not strictly true, because this process is naturally occurring as plants and animals die and become buried under sediment. What we've got to acknowledge though is it's an incredibly slow process. A much faster process is our current rate of consumption. We're consuming fossil fuels at an alarming rate, and the graph here shows the consumption of some countries, China, the United States and India, and you can see how that consumption is continuing to grow. So it's quite clear that the rate at which these hydrocarbons are deposited is much slower compared to the rate at which we're consuming them. So in terms of renewable here, that's a non-renewable process. There's no way that the production of the fossil fuels can be matched by our consumption. And that brings us on to another thought. Antarctica as a continent has perhaps a huge resource of hydrocarbons, not just coal but oil and gas as well. And will Antarctica come under threat with mining companies wanting to harvest hydrocarbons from this continent? Our attention now turns to the ocean as a storage site, and we might say that this offers both long-term and medium-term storage locations. In this section we're going to look at two processes. We're going to look at what's known as a physical pump, where carbon dioxide is moved into the ocean through dissolving, and we're also going to look at what's referred to as a biological pump, and this involves the microscopic phytoplankton that remove carbon dioxide and deposit it as sediments on the bottom of the ocean. Let's begin by looking at the physical pump. And here we're going to see how the deep ocean stores carbon dioxide. We know that the polar seas are incredibly cold, and this is where most carbon dioxide is going to diffuse and dissolve into the water. Of course, the oceans are huge. They have a huge volume, and the hydrosphere can hold 50 times more carbon than the atmosphere. So here we're going to have a look at the formation of Antarctic bottom water. In the winter, sea ice will form, and we can see this taking place in the Ross Sea. And when ice forms, the salinity of the water will increase, because of course ice doesn't contain salt. So that means the water in the Ross Sea becomes saltier and saltier, and this saline water becomes heavier and more dense. The dense water will then sink to the bottom of the ocean. Of course, this dense water is carrying with it carbon dioxide, masses of carbon dioxide. This cold deep water will circulate throughout the world's oceans before eventually re-emerging around the equator, where the carbon dioxide is venting off. So this cold deep water provides a storage site. It's a sink for carbon dioxide, and it will remain here for thousands of years before resurfacing. Some might say that this is a ticking time bomb. So when this resurfaces, even more carbon dioxide will move into the atmosphere. We're now going to look at the biological pump that operates in the oceans. So this is part of the biosphere, not the hydrosphere. We know that in the upper layers of the ocean, the surface of the ocean, there are many small phytoplankton, microscopic plants. And these are doing two things. They're photosynthesizing, so they're taking carbon dioxide out of those upper water layers so that they can grow, and they're obviously providing a food source for other organisms. But they're not only photosynthesizing. Many of these microscopic organisms build for themselves carbonate shells, so they're removing carbon that's dissolved in the water to make a calcium carbonate shell. Now, not all of these phytoplankton are consumed. They're not all eaten, so some of them will fall to the bottom of the ocean and build up on the seabed. And again, over millions of years, we will get these interesting deposits, sometimes referred to as oozes, these biogenic deposits. And here you can see the intricate calcium carbonate shells that these organisms have formed. Over time, these phytoplankton will form layers of shell and sediment, and they're cemented together to eventually form limestone rock. So that limestone rock has a biological component to it. So the carbon containing limestone rock is now part of a very, very slow carbon cycle in the lithosphere. Most of the Earth's carbon is stored in the lithosphere, and you can take time to have a look at this cycle, but you can see that the carbon that started off here as limestone in the oceans may eventually be vented out of the system through volcanoes. Now, we've just talked about sediments in the ocean. What about sediments on land? What about soil? Soil actually holds more carbon than the plants above it. So the detritus in the soil and even the organisms living in the soil are a store for carbon. And I turn your attention back to the nematode worm that you had a look at during the safari. So these worms, not just in Antarctica but throughout the world, are a huge carbon store. Okay, so moving from our nematodes storing carbon in soils, we're now looking at the storage of carbon in plants and phytoplankton. If you think back to pyramids of biomass, we have basically the pyramid building up like so, and we know that this first layer in the pyramid, that shows our primary producers, our plants and our phytoplankton, and by mass there's more of these organisms than the primary consumers, the secondary consumers, or the tertiary consumers. So most of our living biomass, our biosphere, is contained in this bottom layer. Of course, there is carbon in the consumers too, but most of the carbon is stored with the plants and the phytoplankton. Let's begin by looking at forests. Dry wood contains approximately 50% carbon. So through the process of photosynthesis, the plants are a sink because they remove carbon dioxide from the atmosphere. Of course, deforestation has removed vast areas of forest, especially in tropical countries, in rainforests. And by losing this forest, we're also losing a natural sink for carbon. We'd refer to the biosphere as a fast carbon cycle. Of course, photosynthesis is removing carbon dioxide gas from the atmosphere, whereas respiration is putting it back out there. The trees themselves may only last for 100 years or so. So the trees are going to die and decompose, and again the carbon dioxide is going to be cycled really quite quickly in this biosphere. We'd say that the phytoplankton are the forests of the ocean. Although they might be microscopic in size, they make up a huge part of the food chain, and the biomass of carbon in phytoplankton is enormous. This is an electron microscope photograph of diatoms, tiny little phytoplankton that support life in the Southern Ocean. And when conditions are just right, we have these phytoplankton blooms, and you can see that the water here is coloured a greenish sort of a colour, showing you that the phytoplankton is blooming and there's a huge food resource for the rest of the food web. So again, this is a very fast carbon cycle here, with CO2 being removed from the ocean and then being cycled through the food web. Okay, just to summarise, we've looked at the lithosphere as a storage site, a sink or reservoir, and we've seen that as a storage site in terms of soil and sediments, and also as rocks. We've looked at the hydrosphere, and here we've seen deep ocean waters as a source, or a storage site rather, for carbon. And we've also looked at the biosphere as a storage site for carbon in phytoplankton and forests. Sometimes the carbon is stored in these locations for long periods of time. Other times it's much shorter, depending on the processes that are taking place.